Somewhere in a research campus just outside Tokyo, engineers just did something nobody else on the planet has fully pulled off yet. They took one of the most powerful supercomputers ever built, wired it directly into an actual working quantum computer, and got the two of them talking to each other in real time, passing calculations back and forth like two brains solving the same problem simultaneously. This is not a lab demo running on a whiteboard somewhere. It just produced the largest, most accurate chemistry calculation ever performed using a quantum processor. If you have been wondering what happens when quantum computing stops being a theoretical curiosity and starts actually getting bolted onto the world's fastest classical machines, Japan just gave us the clearest answer yet. The machine at the center of all this is called Fugaku, developed by Fujitsu and operated by Riken, Japan's leading national research institute, at its Center for Computational Science in Kobe. Fugaku held the title of the world's fastest supercomputer from 2020 through 2021, an almost unfathomably large machine built from nearly 159,000 individual processor chips, each one packed with 48 separate cores. Even years after losing its top ranking to newer exascale machines built in the United States and Europe, Fugaku remains a genuine computational powerhouse, the kind of billion-dollar system where every single second of uptime carries enormous scientific and financial value. This is the machine Japan chose as the foundation for its most ambitious experiment yet, connecting raw classical computing muscle directly to the strange, probabilistic world of quantum processing. In February of 2025, Riken switched on something that had never fully existed anywhere else in the world before, a working hybrid system pairing Fugaku with a 20-qubit quantum computer called Raimei, built by a company called Quantinuum, using something called trapped ion technology, where individual charged atoms are suspended and manipulated using electromagnetic fields to store and process quantum information. Unlike the more common superconducting qubit approach used by companies like IBM and Google, trapped ion systems allow for something called ion shuttling, physically moving individual qubits around a circuit as needed, which opens the door to more complex, flexible algorithm designs. Riken specifically selected this architecture because of that unique flexibility, and when Raimei came fully online connected to Fugaku, it became recognized as the world's first fully operational, tightly integrated, hybrid quantum supercomputer system, a milestone that other teams around the world, including a group in Germany working with a company called IQM, had been testing toward but had not yet fully achieved in an operational capacity. But Raimei was really just the opening move. Riken's Kobe campus also became home to something else entirely, an IBM Quantum System 2, powered by IBM's 156-qubit Heron processor, using the more traditional superconducting qubit approach that requires cooling components down to temperatures colder than deep space itself. This installation matters for a very specific reason. It marked the very first time IBM had ever deployed one of its Quantum System 2 installations outside the United States, and the very first time one had ever been placed outside of IBM's own dedicated quantum data centers entirely. IBM specifically chose to co-locate the system directly alongside Fugaku, connecting the two machines through a high-speed network operating at what engineers describe as the fundamental instruction level, essentially giving researchers the ability to build genuinely parallelized workloads and extremely low latency communication between the classical and quantum sides of the system. Why would Japan deliberately deploy two entirely different types of quantum hardware, ion trap and superconducting, side by side at the exact same research campus, rather than simply picking one and committing fully to it? The answer comes from a broader, 5-year initiative called the JHPC Quantum Project, launched in November of 2023 as a collaboration between Riken, the University of Tokyo, the University of Osaka, and the Japanese telecommunications giant SoftBank, which is specifically responsible for figuring out how to translate this research into real industrial applications down the road. The entire point of running both quantum architectures simultaneously is to build system software flexible enough to work regardless of which specific type of quantum hardware eventually wins out as the industry matures, essentially hedging against total dependence on any single company's specific technical approach. Leading this effort are 3 researchers whose backgrounds genuinely capture what this project represents. Division Director Mitsuhisa Sato and Deputy Director Uetsu Kodama both previously worked directly on developing Fugaku itself, giving them deep, hands-on expertise in exactly the kind of large-scale classical supercomputing architecture this project needs to interface with. Alongside them sits Deputy Director Tamiya Onodera, who joined this project in April of 2025 after spending more than 3.5 decades working at IBM's own quantum research lab in Tokyo. bringing together people who literally built Japan's fastest classical supercomputer, alongside someone who spent 35 years building quantum systems for IBM, tells you exactly how seriously this collaboration is being taken, blending genuinely rare, complementary expertise from both sides of the classical and quantum computing world into a single unified team. Sato has been remarkably candid about why this hybrid approach matters right now, rather than waiting for quantum computers to mature on their own first. He has explained that while quantum computers can theoretically solve certain problems classical supercomputers genuinely struggle with, today's quantum machines only function usefully when they are actively controlled by conventional computers running alongside them. Current quantum hardware remains noisy, error-prone, and fundamentally limited in scale, meaning it cannot simply operate almost counterintuitive at first. As quantum computers eventually improve by a factor of 10 or even 100 over their current capabilities, the control and communication overhead required to actually operate them will demand even more support from supercomputer-level classical computing resources, not less. In other words, better quantum hardware does not eliminate the need for powerful classical machines working alongside it. It actually increases how much classical computing power gets needed to properly orchestrate and control that improved quantum hardware. If you're enjoying this look at how quantum and classical computing are actually being fused together in the real world right now, go ahead and hit that subscribe button, because we track exactly these kinds of breakthrough research stories every single week. But the most concrete proof that this entire approach genuinely works arrived on January 29th of 2026, when IBM Director of Research Jay Gambetta presented results at a conference called Supercomputing Asia, describing what researchers are calling the largest and most accurate chemistry experiment ever performed on a quantum computer. The joint Riken and IBM research team used the entirety of Fugaku, every single one of its nearly 159,000 chips, working in concert with the on-premises IBM Heron processor, to calculate the electronic structure of a pair of genuinely complex iron-sulfur molecules, the kind of intricate chemical structures that show up throughout biology and materials science, and that classical computers alone have historically struggled to model with full accuracy. The work itself was first described in a paper posted to the Arc preprint server back in October of 2025, and it represents the first demonstration anywhere of quantum and high-performance computing resources working together this tightly and at this scale. What made this specific achievement genuinely novel was not simply that a quantum computer and a supercomputer happened to work on the same problem, but how they worked together. Historically, hybrid quantum classical computing has followed a fairly simple sequential pattern. The quantum processor does some work, hands its results to the classical computer, which does its own separate work, then hands results back, taking turns in a rigid back and forth. The Riken and IBM team built something a closed-loop workflow where Fugaku and Heron continuously exchange data throughout the entire calculation, using an algorithmic approach called sample-based quantum diagonalization. IBM's senior manager overseeing this project, Hiroshi Hori, explained why building this kind of tight orchestration mattered so much. Since both quantum and classical computing resources remain genuinely scarce and expensive, any inefficiency in how a workflow assigns tasks wastes precious runtime other researchers could be using for their own calculations. To solve this, the team built an entirely new task assignment system designed to keep both Fugaku and Heron actively working as continuously as possible, minimizing idle time. This is precisely the part of the story that connects to the idea that classical processing alone genuinely cannot keep up anymore, at least not for certain specific categories of scientific problems. Sato has described how supercomputers, despite their raw power, genuinely struggle in situations where researchers describe something called a computational explosion, meaning problems where the number of possible configurations or outcomes grows so astronomically large that even a machine as powerful as Fugaku cannot realistically explore every possibility within any practical amount of time. Modeling the precise electronic structure of complex molecules like those iron-sulfur compounds is exactly this kind of problem, since electrons within a molecule can exist across an enormous number of possible quantum states simultaneously, something classical computers can only approximate rather than calculate directly and completely. Quantum computers, by contrast, are built from the ground up using quantum superposition, meaning they can represent and process many of these different possible states all at once, giving them a genuinely different kind of computational advantage for exactly this narrow category of problem, even while remaining far too limited and error-prone to handle general-purpose computing tasks the way a supercomputer easily can. That distinction matters enormously for understanding why Japan is not simply trying to build a bigger, more powerful quantum computer in isolation, but is instead deliberately building the connective tissue between quantum and classical systems from the very beginning. As Sato himself has put it, there are countless discussions happening globally about what quantum computers might eventually be capable of a decade from now, but relatively few concrete answers exist for what today's actual currently available. Quantum hardware can practically contribute to real scientific work happening right now. By focusing specifically on tight, efficient integration, rather than simply waiting for quantum hardware itself to mature in isolation, Riken's team is trying to extract genuine, measurable value out of quantum computers as they exist today, imperfect and error-prone as they currently are, rather than treating them purely as a promising future technology still years away from any practical use. None of this exists in a vacuum either, because Japan is simultaneously building the next generation of classical infrastructure specifically designed to support this exact hybrid future. In November of 2025, NVIDIA announced a major expansion of its partnership with Riken, deploying 2 entirely new supercomputers built around NVIDIA's latest Blackwell generation GPU hardware, expected to come online in the spring of 2026. One of these systems, dedicated specifically to AI-driven scientific research, deploys 1,600 NVIDIA Blackwell GPUs using a platform called GB200 NVL4, connected together through extremely high bandwidth InfiniBand networking. The second system, oriented specifically around quantum computing research, deploys 540 additional GPUs, giving researchers dramatically expanded classical computing, muscle specifically to support and accelerate quantum-centric workflows, exactly like the one used in the iron-sulfur molecule experiment. Both of these new machines are explicitly described as bridge systems, platforms specifically meant to help researchers generation supercomputer, being jointly developed by Fujitsu and NVIDIA following an agreement announced back in August of 2025, combines a new processor called Monica X with NVIDIA's latest GPU technology, and it is expected to deliver roughly 100 times greater application performance compared to systems relying purely on traditional CPU-based architecture alone. Fugaku Next is targeted to become operational by 2030, and critically, it has been explicitly designed from the outset with the stated goal of integrating production-level quantum computers directly into its architecture, rather than treating quantum integration as an optional add-on bolted onto an already finished classical system after the fact. Satoshi Matsuoka, director of the Riken Center for Computational Science, has described this entire growing partnership as creating what he calls one of the world's leading unified platforms for artificial intelligence, quantum computing, and high-performance computing simultaneously, specifically designed to help researchers unlock and accelerate discoveries spanning everything from fundamental basic science all the way through practical industrial applications that directly benefit businesses and the broader public. That framing genuinely captures what makes Japan's specific approach here so distinctive compared to how many other countries are currently pursuing quantum research, rather than treating quantum computing as an entirely separate, standalone research track running parallel to classical supercomputing. Japan is deliberately fusing the two efforts together from the ground up, treating quantum processors as a specialized, powerful accelerator meant to plug directly into an already existing, extraordinarily capable classical computing ecosystem, rather than as a completely separate technology meant to eventually replace it outright. Sato has made a particularly bold claim about where this specific effort stands relative to similar work happening elsewhere in the world, stating plainly that his project represents the only global effort currently attempting this kind of large-scale, tightly integrated collaboration between quantum computers and supercomputers at this level of depth. Given how many other countries and companies are simultaneously racing to build increasingly powerful quantum hardware in relative isolation, focused primarily on raw qubit counts and error correction milestones, Japan's specific emphasis on deep, practical integration with existing classical infrastructure represents a genuinely different strategic bet, one focused less on winning an abstract qubit count race and more on proving concrete, measurable scientific value using the imperfect quantum hardware that already exists right now, today, rather than waiting years or even decades for some hypothetical future breakthrough machine to finally arrive. It is worth taking a moment to understand exactly what makes Fugaku such a formidable classical machine in the first place, because the scale involved here is genuinely difficult to picture without concrete numbers attached to it. Nearly 159,000 individual processor chips, each containing 48 separate processing cores, work together across an enormous physical installation that fills an entire dedicated building on Riken's Kobe campus. At its peak, Fugaku delivers roughly 537 petaflops of computing performance, meaning it can perform hundreds of quadrillions of individual calculations every single second. To put that in perspective, a task that might take an ordinary consumer laptop years or even centuries to complete could potentially be finished by Fugaku in a matter of hours or days. And yet, even with all of that staggering raw computational power, Certain categories of chemistry and physics problems remain stubbornly out of reach for a machine like this, precisely because of how quantum mechanics itself works at the smallest scales of matter. It is also worth placing Japan's specific achievement within the broader global race to connect quantum processors with classical supercomputing infrastructure, because Japan is not operating entirely alone in pursuing this particular strategy. Back in June of 2024, a Finnish quantum computing company called IQM integrated a 20-qubit quantum processor into a German supercomputer called SuperMUSI-NG, located at a research center in Garching. That system, however, has remained in a testing phase ever since, without ever reaching the same fully operational, publicly confirmed status that Japan's Fugaku and Raimei combination achieved. IQM has since announced plans to scale that same German integration considerably further, promising a 54-qubit system in the latter half of 2025, followed by an even larger 150-qubit chip sometime in 2026. The comparison matters here because it highlights something genuinely notable about Japan's specific accomplishment. While other nations have been testing similar hybrid concepts for a couple of years now, Riken's combination of Fugaku and Raimei appears to be the first instance anywhere in the world of confirmed, fully operational status, rather than remaining stuck in an extended testing or pilot phase. This is really the central paradox driving Japan's entire hybrid strategy. A supercomputer as powerful as Fugaku can simulate an enormous range of physical phenomena with extraordinary precision, from global weather patterns to the internal structure of new industrial materials. But when it comes to accurately modeling the full quantum behavior of electrons within a genuinely complex molecule, classical computers of any size run into a fundamental mathematical wall. Electrons do not simply occupy one fixed position or energy state. They exist in a superposition of many different possible configurations simultaneously, and the number of these possible configurations grows exponentially larger as you add more electrons and more atoms to the molecule being studied. A classical computer, attempting to fully and precisely track every single one of these possible configurations for a moderately complex molecule, would require more memory and processing time than could ever practically exist, even using a machine as powerful as Fugaku. Researchers typically get around this limitation using various approximation techniques, but those approximations inevitably sacrifice some degree of accuracy in the process. Superposition of states naturally, since qubits themselves rely on the exact same underlying quantum mechanical principles that make electron behavior so difficult for classical computers to simulate in the first place. In theory, this makes quantum computers a naturally elegant tool for modeling molecular electron behavior with far greater precision than classical approximation methods typically allow. The challenge, of course, is that today's quantum computers remain small in scale and prone to errors, meaning they cannot yet handle an entire complex calculation completely on their own from start to finish. This is precisely the gap that Japan's hybrid approach is specifically designed to bridge, using the quantum processor to handle the specific piece of the calculation that genuinely benefits from quantum mechanical representation, while relying on Fugaku's overwhelming classical power to handle everything else, including the substantial overhead required for error correction, calibration, and the broader coordination of the overall calculation. Understanding the iron-sulfur molecule experiment in a bit more technical detail also helps clarify why this specific result generated so much excitement within the scientific community. Iron-sulfur clusters are a genuinely important class of molecular structures found throughout biology, playing a critical role in numerous biological processes, including cellular respiration and photosynthesis, and they are notoriously difficult to model accurately using classical computational chemistry methods alone, precisely because the iron atoms involved have complex electron configurations that produce exactly the kind of exponentially large superposition problem described above. When the Riken and IBM team used their hybrid Fugaku and Heron system to tackle this exact problem using the sample-based quantum diagonalization method itself represents a genuinely clever middle ground between pure classical and pure quantum computation. Rather than asking the quantum processor to calculate the entire electronic structure of the molecule in one single operation, which would require far more qubits and accuracy than today's hardware can reliably deliver, the method instead uses the quantum computer to generate a large number of individual quantum samples, essentially many different possible snapshots of how the molecule's electrons might be configured. These samples are then passed over to Fugaku, which uses its own massive classical processing power to analyze, filter, and mathematically diagonalize this large collection of samples, finding the most likely and most accurate overall picture of the molecule's true electronic structure. This is exactly the kind of task where quantum and classical computing genuinely complement each other rather than working on entirely separate pieces of the same problem independently. If you are enjoying this deeper technical look at how these hybrid systems actually function under the hood, go ahead and hit that subscribe button, because we regularly dig into exactly this level of detail on the biggest breakthroughs happening across quantum computing and high-performance computing research. It is also worth examining more closely why Japan specifically chose to deploy two entirely different types of quantum hardware side by side at the same research facility, since this decision reflects a deeper strategic philosophy that goes beyond simple technical redundancy. Trapped ion systems like RIMI and superconducting systems like IBM's Heron each come with genuinely different strengths and weaknesses that matter enormously for different types of calculations. Trapped ion qubits tend to maintain their quantum state for considerably longer periods before succumbing to environmental noise, property researchers call coherence time, which can be extremely valuable for calculations requiring many sequential steps performed in careful order. Superconducting qubits, on the other hand, tend to perform individual quantum logic operations considerably faster, though they typically lose their quantum coherence more quickly as a trade-off. By maintaining active research programs using both approaches simultaneously, Riken's team can directly compare how each architecture performs on the exact same categories of scientific problems, building genuinely comparative expertise rather than betting the entire national research program on a single technological approach that might later prove less effective than a competing method. This also serves a longer-term software development purpose, since the JHPC Quantum Project's underlying system software aims to create a genuinely hardware-agnostic layer that lets researchers write quantum classical hybrid algorithms without needing to completely rewrite their code, depending on which specific type of quantum processor happens to be available, an approach that matters enormously given how rapidly the underlying hardware technology itself continues evolving. Beyond the immediate technical achievements, it is worth considering the broader institutional and financial commitment Japan has made toward this specific vision of hybrid quantum classical computing, because the scale of investment involved reveals just how seriously the country is treating this strategic bet. The JHPC Quantum Project itself represents a 5-year, multi-institutional commitment bringing together some of Japan's most prestigious universities, alongside one of its largest and most influential technology and telecommunications companies. Layered on top of that is Riken's ongoing expanding partnership with NVIDIA, involving the deployment of thousands of cutting-edge graphics processing units specifically dedicated to accelerating scientific computing and quantum research workflows. And beyond even that, the entire Fugaku Next program represents a multi-year, multi-billion-dollar national infrastructure project explicitly designed with quantum integration built into its core architecture from the very beginning, rather than treated as an afterthought bolted on once the classical portions of the system were already finished and operational. This kind of sustained multi-layered investment stands in interesting contrast to how some other nations have approached quantum computing research, often through a larger number of smaller, more fragmented individual grants and pilot programs spread across many different research institutions and companies, each pursuing somewhat different and occasionally competing technical approaches. Japan's specific strategy, by comparison, appears considerably more centralized and coordinated, concentrating expertise, computing infrastructure, and long-term institutional commitment around a single, unified research campus in Kobe, with clear stated goals and a defined multi-year roadmap stretching all the way out to the planned 2030 debut of Fugaku Next. It is also worth stepping back to consider how this entire story fits into the much larger global context of quantum computing, across the United States, China, Europe, and elsewhere throughout 2026. Many of the highest profile headlines surrounding quantum computing over the past several years have focused heavily on raw qubit counts and increasingly dramatic claims about quantum computers outperforming classical machines on narrow, specialized benchmark tasks, sometimes with limited, immediate practical application beyond demonstrating the underlying physics works as theoretically predicted. Japan's specific approach, emphasizing deep practical integration with existing classical supercomputing infrastructure aimed at solving genuinely useful scientific problems like molecular chemistry calculations, represents a notably different emphasis, one focused less on abstract technical milestones and more on demonstrating concrete, immediately applicable scientific value using quantum hardware that already exists today, however limited and imperfect that hardware currently remains. This distinction matters because it suggests two genuinely different paths toward quantum computing, eventually delivering real-world value at scale one waiting for quantum hardware itself to mature dramatically before operating independently, and the other, the path Japan appears to be betting on most heavily, extracting genuine measurable value out of today's imperfect quantum hardware right now through careful, sophisticated integration with existing classical infrastructure. What makes Japan's specific contribution to this broader global effort genuinely noteworthy is the fact that it has already produced a concrete, published, peer-reviewable result, the iron-sulfur molecule calculation, rather than simply describing a promising theoretical framework that has not yet been tested at meaningful scale. That distinction between theory and demonstrated practice matters enormously in a field that has occasionally struggled with a gap between ambitious announcements and genuinely reproducible, independently verifiable scientific results. Looking further ahead, the planned expansion toward Fugaku Next by 2030 suggests this entire research program is still in its early stages rather than approaching any final mature form. The two new NVIDIA-powered bridge supercomputers arriving in spring of 2026 will spend the following years helping researchers refine exactly how classical GPU acceleration can best complement quantum processing within this broader hybrid framework, building toward the eventual debut of a fully integrated system designed from its earliest planning stages to incorporate production-level quantum computing hardware as a core foundational component. If Japan's research team continues producing genuinely useful results at the pace demonstrated by this iron-sulfur molecule breakthrough, the country appears well positioned to remain among the genuine global leaders in practical, application-focused quantum computing research throughout the remainder of this decade. It is also worth understanding why this kind of hybrid integration is considered necessary at all, rather than simply waiting for quantum hardware itself to mature into something powerful enough to stand entirely on its own. Today's quantum computers, regardless of whether they use trapped ion technology like RIME or superconducting technology like IBM's Heron processor, remain fundamentally limited by a problem researchers call noise. Individual qubits are extraordinarily sensitive to their surrounding environment, and even tiny, practically unavoidable disturbances can introduce errors into a calculation. Scientists are developing increasingly sophisticated error correction techniques to compensate for this noisiness, but those techniques typically require significant additional computational overhead to implement effectively, which is precisely where the classical side of a hybrid system becomes essential. A powerful classical supercomputer like Fugaku can handle exactly this kind of error correction and calibration overhead, keeping an inherently noisy quantum processor productively contributing useful results, rather than simply generating unreliable noise of its own. There's also a genuinely practical, real-world commercial dimension driving this entire effort forward, one that goes well beyond pure academic curiosity. SoftBank's specific involvement in the broader JHPC quantum project reflects a deliberate bet that this kind of hybrid quantum classical computing approach will eventually translate into genuine industrial applications with real commercial value, rather than remaining confined purely to government-funded academic research indefinitely. Molecules similar in structural complexity to those iron-sulfur compounds calculated during the recent experiment play meaningfully important roles across pharmaceutical drug discovery, advanced battery chemistry research, and the development of new industrial catalysts. If hybrid quantum classical systems can reliably model these kinds of complex molecular structures with accuracy classical computers alone consistently struggle to match, the practical applications extend well beyond an academic paper, pointing directly toward faster drug discovery pipelines, improved battery technology for electric vehicles, and more efficient industrial chemical processes across sectors where Japan has historically maintained significant global industrial strength. Whether this specific hybrid strategy ultimately proves to be the winning long-term approach compared to other nations, pursuing more isolated, quantum-first strategies, remains a genuinely open question that will likely take years to answer. But the underlying achievement itself, a billion-dollar supercomputer working in tight, continuous coordination with an operational quantum processor to solve a genuinely difficult, previously intractable chemistry problem, represents a real measurable step forward rather than another promising research paper describing what might theoretically become possible someday. Classical computing alone genuinely could not efficiently solve that specific molecule problem within any practical amount of time. Quantum computing alone remains far too limited and noisy to solve it independently either. It took both systems working together, continuously exchanging information in real time, to actually get the job done. So what does this entire story actually add up to, beyond simply one impressive chemistry calculation performed using an unusually powerful combination of hardware? It represents a genuinely different philosophical approach to quantum computing's near-term future, one that treats today's admittedly limited and imperfect quantum hardware as a valuable, specialized tool worth carefully integrating into existing classical computing infrastructure right now, rather than as a standalone technology whose true value remains locked away until some distant future breakthrough finally arrives. Japan built the connective tissue first, the sophisticated system software, the tightly coupled hardware architecture, and the specialized interdisciplinary research team, specifically so that whatever quantum hardware breakthroughs eventually do arrive. Over the coming years and decades, the country already possesses the infrastructure and expertise needed to immediately translate those breakthroughs into genuine practical scientific and industrial value, rather than starting that integration process from scratch only after quantum hardware itself finally reaches some hypothetical point of full technical maturity. There is a broader lesson buried in this story too, one that extends well beyond Japan's specific research campus in Kobe. For years, public conversation around quantum computing has framed the technology as a distant, all-or-nothing future event, a moment when quantum machines will supposedly replace classical computers outright once they finally become powerful enough. What Japan's hybrid system actually demonstrates is a considerably more realistic path forward, one where quantum and classical computing resources coexist and reinforce each other rather than competing for the exact same role. Rather than waiting for some distant future tipping point, Riken's approach suggests that meaningful, measurable quantum advantage may arrive gradually through exactly this kind of careful, deliberate integration work, long before quantum computers ever become powerful enough to operate as fully independent general-purpose machines in their own right. If this kind of deep dive into how quantum and classical computing are actually being combined in real, working laboratories right now is exactly the content you want more of. Make sure to like this video and subscribe, because we will keep following this story as Japan, the United States, and the rest of the world continue pushing this hybrid approach further in the years ahead.